I'm going to do an exercise on a conditional distribution that deals with binomial and Poisson random variables. We know what a binomial random variable is, hopefully, and we know what a Poisson random variable is. What is the support of a binomial? 0 to n. Support of Poisson? 0 to infinity. And what are the things that we need for a binomial? N and P. And what do we need for Poisson? Lambda. So here is an example. I guess it'll be easier to understand if we use an example. So the coffee shop doesn't make the same number of muffins every day. Rather, the number of muffins made at a coffee shop is distributed as Poisson, and the average rate is lambda, so we'd make lambda per day. Lambda could be some number, and lambda becomes the parameter of our Poisson distribution. Now, let x be the number of muffins sold and y be the number of muffins wasted, in other words, not sold. So naturally, x plus y must equal n. Suppose I have some x number of muffins that are sold per day, and I condition on n, some fixed value n. And I also define P is the probability that a muffin will be sold. Good. So P is the probability that a muffin is going to be sold. X would be the number of muffins that are sold. Y, number of muffins that are wasted or not sold. N is the number of muffins made at a coffee shop. Now, if I simply said x plus y is a fixed number, then what distribution would it have? Huh? Bernoulli. Binomial, right? Right, you have n of it, correct? So if this happens to be a fixed number, and I made, say, 20 muffins, I can say the number of muffins sold per day is going to be distributed as binomial, n over p. But that's not a fixed number, right? Because n is a random variable. And that random variable is distributed as a Poisson. So I cannot say that x will have a binomial distribution. Does that make sense? So if I change the problem and said, let me condition on n equals some fixed value n, then what would the distribution of x be? Binomial. What is the parameters here? P and n or n and p, doesn't matter, right? In a similar manner. If I said y and conditioned on n equals n, very good. Binomial and q. Yes? But wait. So that happens because I'm conditioning on some single value. Mary, did you have a question? So a single value, which could be 150, whatever. How many such n's would we have in this problem if we have to write it out? Do you follow my question? I fixed on some single value. In other words, I have conditioned on n equals something. My question to you is, how many such lowercase n's are possible? Infinite, because it's a plus or minus variable. So, do you really want to sit and write them all out? No, absolutely not. Okay, so what would the joint distribution of x and y look like? Well, this joint distribution is only going to work under one condition. And what is that one condition? I plus j equals n. So what we can do is I can say sum n equals 0 to infinity, probability of x is equal to I, y equals j, given n equals n, multiplied by probability of n equals n. That's why I asked that question as to what are all the possible values for such little n's, and you guys said infinite, because n is Poisson. That sum comes from something we already know. We mentioned it today earlier. That sum should look like something. Very good. This is simply the law of total probability again. So I'm conditioning on some random variable and summing it over all possibilities of that random variable. So once again, this becomes the law of total probability. Even though I have that stuff, I am going to argue this entire sum is going to work for only one value of n. What is that one value of n? So this entire expression would then become x is equal to I, y equals j, given n equals I plus j multiplied by probability of n equals I plus j. Should I worry about both I as well as j in this problem? Or should I just look at I and be happy with it?
Well, at this point, they're sort of like one and the same, like if they add up to equal. And
right, so if I condition it on I plus j, so one simply will be the complement of the other, right? If one is x, the other is going to be n minus x. So I could simply write it as probability of x is equal to I, given n equals I plus j. And the entire conditional part is simply telling us that this is true because I have set n to be one fixed value, and that one fixed value is I plus j. We know the distribution of a binomial. So conditioned on n, we know that this is binomial. That's what I wrote over here. Yes? And we know that that is Poisson. Correct? We know the PMFs of both. So I want you to use those two and see what expression you get. But before we even get to that, something happened when I went from here to there. What is that something? Huh? Y plus j goes away. What would that mean in a practical standpoint, Mary?
I mean that I and they are the same. You're under the assumption that they're the same.
Okay.
We go from a joint PMF to just a regular PMF or a conditional PMF.
So what does that say about x and y? Suddenly they are July 4th. Independent. Right, yes.
And we get rid of the like little j, or I and j are kind of related.
Yes, right. If I fix x, then that would simply be n minus x. Okay, so I'm going to erase this side. N is Poisson lambda, x plus y, n, and p is probability of success. X given n equals n is binomial, so that part is binomial I plus j, comma p. Yes? The second part is Poisson, so we're just fixing it on one single value. So I could write the joint distribution. I plus j, choose I, p raised I, q raised I plus j minus I, times Poisson evaluated as one single value, I plus j, so lambda raised I plus j, e raised minus lambda, divided by I plus j. That's all. Yes? Those two would go away. I plus j, choose I plus j factorial, divided by I factorial, j factorial. P raised I, q raised j. Lambda raised I times lambda raised j. E raised negative lambda divided by I plus j factorial. Yes. That term will go away. I can combine the lambdas, yes. Excuse me, lambda and the p, lambda and the q. So probability of x is equal to I, y equals j, lambda p raised r, lambda q raised j, I factorial, j factorial. Most of you got this far, very good. We're almost there, right? That should remind you of some distribution, at least part of it. Peter? It's a Poisson distribution. Now, what are we missing?
We're missing another either than lambda.
I'm missing e raised negative lambda. But is it truly e raised lambda though?
Lambda p and lambda q.
Lambda p and lambda q. How am I going to get lambda p and lambda q from lambda?
E plus q.
Easier than that. Right, top braces then. P plus q is 1. Yes.
Yeah.
We know that P plus q is 1. Now I can split it up.
So that's subtraction.
Wow.
Or is it an equal sign?
Oh, sorry, that's an equal sign. So I can split the exponential and write it as lambda p raised I over I factorial, lambda q raised j over j factorial, e raised minus lambda p times e raised minus lambda q. Going to shuffle things around, and lambda p raised I over I factorial, e raised minus lambda p, lambda q raised j divided by j factorial, e raised minus lambda q. Yes? I is purely related to the values of x. Do we agree? And what j is purely related to the values of y. Correct? So, by all means, whatever we computed here would be the probabilities for x. Yes? And that would be the probabilities for y. So, what happened here is I was able to I put it in square brackets to show that I split them or partition them into perfect PMFs, right? So I took a joint PMF and I split it up into perfect marginal PMFs. So this would be probability of x is equal to I, and that is probability of y is j. What are the distributions of x and y? X is Poisson lambda p, and y is Poisson lambda q. And also, x and y are independent. If you can split the joint distribution and write it as a perfect product of two valid marginal PMFs, then you have independent. Yes. You can extend this to n different random variables also. Now, what do we know about sum of Poisson random variables? If I sum two Poisson random variables, the result is Poisson, and what is its parameter? Suppose if I had lambda 1 and lambda 2. Lambda 1 plus lambda 2, yes. Well, this would simply mean x plus y will be Poisson lambda p plus lambda p. And we just showed x, y are independent, x and y are independent. What happens to that term? Factor of the lambda, p plus 2 is 1. This would reduce to lambda. But what is x plus y then? So it satisfies our original assumption. So what did we show? If we start with a Poisson lambda, then if I condition on n, the individual variables would end up becoming binomial if we have a probability of success. We will have x and y end up being independent, and each of them would have a Poisson distribution. So Poisson lambda p, Poisson lambda q. Good. Put them together, Poisson lambda. Condition on n binomial. Good.